We're going to look at some common ion solutions. Examples include a solution of a weak acid plus the salt of the weak acid, or a weak base plus the salt of the weak base. These are also called buffer solutions because they resist changes in pH. So for example, we have a solution that contains acetic acid and sodium acetate. Sodium acetate, when put in solution, breaks apart into ions. And so sodium acetate gives me a concentration of the product in this example equation. And so that provides a high concentration of acetate ions, which shifts the equilibrium to the left according to Le Chatelier's principle. And as a result, the concentration of H3O goes down in a common ion solution. Let's look at an example. Calculate the concentration of H3O and the pH of a solution made from acetic acid and sodium acetate. First thing I need is an equation. So we're going to start off with my weak acid plus water forming H3O and acetate. Icebox. Initial concentration of the acetic acid is 0.5. H3O is 0. Now I have a salt here, so that's going to give me a concentration initially of 0.4 for acetate. So the 0.4 comes from sodium acetate. Then we're going to do the change. We don't know the equilibrium, so we'll do X's. And we'll set up our Ka expression. Ka is 1.7 times 10 to the negative 5. It's going to be equal to X times 0.4 plus X divided by 0.5 minus X. And just like we were doing before, we can assume X is negligible because Ka is 10 to the negative 5th or less, and we're starting with a concentration greater than 0.01. So we'll assume X is negligible, and our Ka expression will look like this. 1.7 times 10 to the negative 5 would be equal to X times 0.4 divided by 0.5. So we get rid of plus X and minus X. We're going to solve for the concentration of hydronium. And hydronium comes out to a concentration of 2.1, 10 to the negative 5 molar. And then the pH is the negative log of that, so the pH comes out to 4.68. So you can see that that common ion reduced the concentration of H3O from 2.9 10 to the negative third down to 2.1 times 10 to the negative fifth. So common ions reduce the concentration of H3O. There's a useful equation that can be derived. I'm not going to go through the derivation process, but the Henderson-Hasselbalch equation will work if I want to determine the pH of a buffer solution. pH is equal to pKa plus log of salt over acid, where pKa is the negative log of Ka. There's also a similar form for a weak base and the salt of a weak base, solving for POH. I'll go through one problem with the Henderson-Hasselbalch equation, but I'm not a big fan of it. You can use it if you wish, but I prefer to use the icebox method. So in this problem here, calculate the pH and the POH of a solution that's got a weak base, NH3, and the salt of the weak base, NH4Cl. So since we have a weak base and the salt of the weak base, I will use this form of the Henderson-Hasselbalch equation. And this will allow me to find the POH. So the POH is equal to pKb, which is negative log of the Kb, which is 1.7 times 10 to the negative 5, plus log of the concentration of the salt. Well, the salt here is NH4Cl, divided by the concentration of the base, which is 0.2. So when you solve this, you will get the POH from the Henderson-Hasselbalch equation, which comes out to value of 4.47. And then if I want the pH as well, let's take 14 minus 4.47. So the pH, 9.53. When you use the Henderson-Hasselbalch equation, it is assumed that X is negligible. So you can use the Henderson-Hasselbalch. I just prefer to use the icebox method. You will get the same answer regardless of which method you choose to use. Buffer solutions or common ion solutions resist changes in pH. They do this by reacting with both hydronium and hydroxide ions. So let's look at this example here. We have a buffer solution of acetic acid and sodium acetate. What is the pH of this solution? I need an equation. So acetic acid, that's my weak acid, reacts with water. I get hydronium and acetate. Icebox. Initial for acetic acid is 0.1. Hydronium is 0. Acetate comes from sodium acetate, which is also 0.1. The change, just X. And I know that Ka is 1.7 times 10 to the negative 5, so I can use the shortcut. So let me move to the next slide. I'm going to apply the shortcut. Ka, which is 1.7 times 10 to the negative 5 for acetic acid, is equal to X times 0.1. That's the products, divided by just 0.1. I got rid of the plus X and minus X. And so X, which is the concentration of H3O, comes out to a value of Ka in this case, 1.7 times 10 to the negative 5. We want to calculate the pH. So pH would be negative log of 1.7 times 10 to the negative 5. So pH comes out to 4.77 for this buffer solution. Buffer solution resists changes in pH because if I add a small amount of H3O, it's converted to acetic acid. If I add a small amount of OH, it will neutralize the H3O, but the acetic acid will dissociate and maintain the pH fairly constant. So let's look at part B of this problem. We had my buffer solution. Now we're going to add NaOH to the buffer solution. What will the pH be after I add NaOH? Okay, here's my equation. Okay, the buffer solution, we had a concentration of 0.1 for acetic acid. My H3O was 1.7 times 10 to the negative 5 molar, and my acetate ion was also 0.1. These are the concentrations in the buffer solution. After I add NaOH, I want to see what's going to happen to these concentrations. Well, NaOH is a base. That's going to react with the acid. Well, the acid in this buffer is acetic acid right here. So if the base reacts with the acid, the concentration of the acetic acid is going to go down, and it's going to go down by 0.01. So after I add NaOH, my concentration of acetic acid will be 0.09. I'm simply subtracting 0.01 moles. I'm assuming 1 liter of solution. I'm going to subtract from the acid side. The base here is the acetate ion, and I'm going to add 0.01 to acetate. So 0.11 over here, and I want to find out what H3O is equal to, because I want to find the pH of the resulting solution. So my Ka expression now looks like this. Ka is 1.7 times 10 to the negative 5. That's equal to X, which is H3O, times 0.11 divided by 0.09. X is concentration of H3O. When I solve, concentration of H3O comes out to be 1.4, 10 to the negative 5 molar. And so the pH, after I add a strong base to this buffer solution, the pH goes up to 4.85. The pH of the buffer solution was 4.77. It went up to 4.85. So the pH was maintained fairly constant even after adding a strong base to the buffer solution.